Now the third component, which is a register, let's talk about this. This is like used as a 1-bit storage element. So probably you remember we constructed a flip-flop, right, in a couple of lectures down the line. Sorry, previous 1 or 2 lecture, right? We built up a flip-flop, and you may ask like, hey, a flip-flop stores a bit, right? What needs to be done on top of that? Now imagine a computing system. There are different component and parts, and there can be situations where one module is generating informations in terms of series of bits, and like let's say 32 bits and series of them on a timeline, and it is targeted towards different modules, but not always at all of them. Like let's say your data generation is coming from module A, and module A can send data to either module B or module C or module D, right? Now, and those modules need to store that data. Now, this A is sending out data. That data line is connected to module B, C, and D. And if we use flip-flop as a storage device, that means upon that active edge, let's say it is a positive edge trigger flip-flop. So upon the positive edge, all the modules B, C, D, they will store that data. There is no way for module A to send selectively data to module C, for example, or some other time instance it's module D, or both module B and D but not C, something like that, right? So to do that, we need to have build a like selection capability in the storage, that whether the incoming data is for me or not. Like just think from module B, module C, or module D perspective, that it needs to, some extra signal needs to be come into them in order to like latch or load that data into it, otherwise it will not load it. So that's what we do through a register. Let's talk about 1-bit register. It looks like a flip-flop, at least interface wise. Mostly, like there can be preset, reset, Q, Q bar, clock, D, and extra input is L. L stands for load or latch, whatever you want to imagine. So if L is 0, D won't be stored inside this module, okay, inside this component. Only if L equals 1, then it stores the incoming value D into it. So how is it implemented? It is implemented using 2x1 1-bit mask mux multiplexer. So here it goes like we use a D flip-flop, which has preset, reset, clock, Q, but D, and then we include a mux on that, and let's say on the 0 signal, selection signal value 0, I load back the internal flop value itself. Okay, the Q is connected to terminal 0 and D is connected to terminal 1, and output of the mux goes to the D of the flip-flop. Preset reset goes directly into the flip-flop, and clock also directly go into the flip-flop. Now signal L is the selection signal for that multiplexer. So what happens if L is 0, then the previous value of the current value of the Q will go as a next state, right? So if the Q was 0, it will again relatch that value 0. If Q is 1, then it will relatch the value 1. Only if L is 1, then this multiplexer will send the data, whatever D is incoming, that B, into that flip-flop. So let's say Q was 1, D is set to 0, and L is set to 1. Then this clock cycle, this flip-flop will latch that 0 and Q will be set to 0 at the end of the cycle. So, and we can do the same like analogy with if D is 1, Q is 0, and we see that bit change, etc. But point inside is this: we are using multiplexer and flip-flop in conjunction together so that we can select between whether to load a specific data onto this storage element or not. Together we call this is a register. This is a 1-bit register. We can register data into it depending on whether we want to load it or not. Okay, selectively register data. So this is register. So you can well imagine how we can do a multi-bit register. Like when we talk about like 32-bit register, it has 32 1-bit register inside it. Okay, like 16-bit register, it has 16 1-bit register inside it, and its connection is very simple. Let's do it for 4-bit register, and you can well imagine how we can extend it to like 6-bit or 8-bit or 16-bit or 24-bit, whatever number of bit. It's the same idea. So let's place 4 such register and mark their output as Q0, Q1, Q2, Q3. So they are like LSB to MSB. We just put that in the order. They share the same clock. They share the same load signal. Okay, its clock and load are common to all these registers. Only the incoming data, let's say 4-bit incoming data, D0, D1, D2, D3, they are respectively connected to those individual registers. That means you can send a 4-bit information into this big whole component and set the load to 1. Then what happens? This 4-bit information will be stored into these individual registers as 1 bit each and reflected back into your output of that register, 4-bit register Q0 to Q3. So that's a general concept how these registers are built up from basic gates, right? So you can well imagine a 4-bit register has 4 1-bit register. Each of the 1-bit register has one D flip-flop and one 2x1 1-bit multiplexer. Inside 1-bit 2x1 1-bit multiplexer, it has this 1 to 2-bit decoder and selection logic and so on and so forth. Those are all logic gates, and inside the flip-flop, if you recall, it has all this master and slave latches, D latches, SR latches, and then you can imagine like each of this logic gate has its transistor PMOS and NMOS, right? So it looks like a simple from the outside, but if you drill it down till the device level, electronic component level, it becomes complicated and complicated and complicated, right? So we need to be clear about those whole concept, and we should be very fluent in thinking that okay, from this upper level abstraction till the device level, like we can go to and fro, like okay, given a register, it becomes like 4 1-bit register. Then inside 1-bit registers, each of them has multiplexer and this, and inside multiplexer it has this, inside flip-flop this has this, and we just drill it down and expand, okay, in the different abstraction level. So this is like multi-bit register. Now let's talk about something like a shift register. Okay. Shift registers are, remember, like register has this ability to shift left and right, shift left logical SLL, shift right logical SRL, that kind of instructions, and how we can implement it. So let me introduce you with some special type of register called shift register. To start with, let's forget about the 1-bit registers. Let's just deal directly with the flip-flop. Okay, so there are 4 flip-flop and 4 of them are connected in a daisy chain fashion. What does it mean? One, like output from one flip-flop goes to the input of the next flip-flop. and so forth. Then finally it goes out as a SO, and the first stage flip-flop D signal is connected to something called SI, and they all share the same clock, CLK. So SI stands for scan in and SO stands for scan out. Just for your information, it is more related to the digital testing and built-in self-test and all these techniques, but not important for this class. Important is to understand this concept, what is going on in this shifting of register. So the function is this: as the clock keeps on toggling 0 and 1, and let's say per clock cycle one new bit is coming in into the SI, some other driver or device is actually sending out some bit pattern into it. So clock by clock it will go and store each of the bit on this first stage flip-flop, and that same cycle this first stage flip-flop output will be stored in the second stage output will be stored in the third stage stage output will be stored in the fourth stage. So as if this incoming bit is being becoming shifting towards from SI to the SO terminal. Like it is each clock it is shifting the values. And remember, like we in the lab section we have implemented this ripple counter towards the same similar connection fashion, right? This toggle flip-flop and one toggle flip-flop goes to the another, and so on and so forth. Like, so it's not really the daisy chain connection, but the concept is kind of a similar, like each toggles with the clock as an input from the previous stage Q, right? Previous stage Q output. So it's a similar fashion. So I believe the Q was connected to the clock of the next stage in that toggle registers, like that thing. But here we are having the clock as is independent. It is feeding in all the flip-flops, but scan in goes to the first stage, and then successive stages are connected in a daisy chain fashion. And last stage of the flip-flop gives you the output as a scan out port. So from this concept, let's do this. Like from that, now what we want to do is to control the shift. Okay, so in this configuration you cannot control the shift. You can, whatever is incoming you have to take, and you have to go and then keep on shifting the bits and send it out, right? Now, is there a way I can selectively pick up some incoming bit? Otherwise I'll hold on to this bit pattern, whatever right now is happening. So we can do that. Use couple of multiplexers there, 2x1 1-bit multiplexer, where scan in goes into the terminal 1 of the, let's say, first stage multiplexer, and Q from the first stage flip-flop comes back to the 0 terminal of the first stage multiplexer, and output of the first stage multiplexer goes to the D terminal of the first stage flip-flop. And then the same Q of the first stage flip-flop goes into the terminal 1 of the second stage flip-flop, and second stage flip-flop terminal 0 is connected to the second stage flip-flop's Q, and output goes to the D of the second stage flip-flop, and so on and so forth. It has this whole connection, and all the selection of all this multiplexer is a common shift signal. Okay, shift signal. So what happen if shift is 0 at this point? Shift is 0 at this point. Then what will happen? All this multiplexer will select the terminal 0 to send out to D, which is like as if we are giving a feedback from one flop to itself, right? From first stage Q will go through the multiplexer and being fed back into the its own D. Similar second stage flip-flop Q will go back to its own D. Similarly third stage, similarly fourth stage. Now, if shift is 1, then it's a different story. Then your scan in will come into the first stage. Second stage will be driven by the output of the first stage. Third stage will be driven by the output of the second stage, and it becomes just like this operation of this. Just so essentially what we achieved here is a selective shifting. Like this SI can be independently toggling per clock, doesn't matter. As long as the shift is kept 0, I'll keep the value as it is. As soon as we make the shift as 1, then we start with the incoming bit, and those are doing shifted through this series of flip-flop and ultimately goes out through the scan out. With that, then what happens, now you see this combination of a flip-flop and a multiplexer, and we already know what this is. This is a 1-bit register, right? This is a 1-bit register, and that's what we now can replace it in our shift register structure. Okay, now we are coming with a this. Okay, we, instead of placing individual flip-flop, now we place registers, 1-bit registers. And we can of course do some like individually also bring out the individual registers output as a port, and then this shift signal is connected to the load of each of this register, and SI is connected to, let's call the left side as our own convention. That's the LSB side, and right hand is the MSB side. So SI is connected to the LSB side of the register of these 4 registers, and values are trickled down in a daisy chain fashion through the registers. They are connected in a daisy chain fashion. So what happens now? You can selectively start shifting the incoming bit pattern through this chain of flops, and you can observe those values, all of them, is just not that last MSB stage is out as a scan out, but you can observe all the output and make it a 4-bit information for some other modules, or if you need it, right? But the basic concept is that you are now connecting register in a daisy chain fashion to selectively shift incoming bit pattern through 1 bit. Okay, one of the input bit scanning. Now let's work on to this concept. Okay, now we want to do more. So this is simple. I am like simply incoming bits I am shifting through, right? That means I have a hard time to set this 4-bit in a specific bit pattern, right? I will need to send out, like whoever is generating the bit pattern in SI, send out that specific bit pattern in 4 successive cycle and being loaded into these 4 registers. So initialization of this register to a particular value, I cannot load it directly, right? I cannot load say a 1011 pattern, right? 1011 pattern. What I need to do, shift in 1 first and 0 first, and then 1 and 1, and then after 4 clock cycle it becomes 1011. I don't want to do that. I want to make a parallel load. I want to load with a predefined bit pattern and then want to shift. So what happens here, we can still do it. So let's say I have couple of modes in my this register. Let's talk about 2-bit register, and then we can extend to 4-bit, 8-bit, 16-bit, 32-bit, same concept. So let's say I have couple of modes, and mode is determined by two independent input M1 and M0. 0011 is my hold, and 01 is my serial shift right, and 10 is my parallel load. Okay, so essentially this register we are doing a 2-bit shift register, but it can only shift to the right. Additionally, it can load a data 2-bit directly. Okay, so we have a scan in, we have a scan out from, let's say, Q0. It doesn't matter where I actually put the scan out, label it as a scan out, but let's concentrate on this Q1 and Q0. And this mode is practically selecting values incoming line of 4x1 1-bit multiplexer. So I have two of them for two of these flops. Remember, this is flop, this is not a register, this is flop. And we have, let's say, two parallel input like D1, D0. So that means in my 10, if I set M to 1 and M0 to 0, this D1, D2 will be loaded into these two flop and reflected in the output Q1 and Q0. So what will happen now? Let's talk about the hold mode. Okay, so 0011. So this mode M0, M1 goes as a selection of these two multiplexer, and Q1 is, let's say, feedback into my flop. So where it will be need to be feedback into its own in the mode 0 and mode 3, right? So if the selection is 1 1 or 0 0, so terminal 0 and terminal 3 are set as a feedback from its own, like for both of this flip-flop. And then scan in mode, which is serial shift right. So 0 1 means your selection terminal is 1 now. So scan in goes into, let's say, that flip-flop with the Q1 terminal 1, and Q1 is connected to the terminal 1 of the other flop, other multiplexer. Now this will become shift right from MSB to LSB. It is shifting towards the right, so it's a shift operation. Now parallel load, which is like 10 terminal 2, so we'll just connect this D1 to the two of this upper multiplexer, and D0 to the terminal 2 of the lower multiplexer. Then in this mode, if we do a 1 0, M1 equal 1 and M0 is 0, then your D1 will be loaded into the flip-flop, and flip-flop for Q1, and D0 will be loaded into the flip-flop for Q0. So that becomes your parallel load. Now from here, so this is the whole shift register, 2-bit shift register. So you can extend, well, imagine how we can extend it for 4-bit. So you need to have like 2 more multiplexer, 2 more flip-flop and connections, and then from there to 8-bit and so on and so forth, right? So you can do that. Now I want to also not only the shift right, can I do a shift left as well? We can do it. So remember, like we have like both the hold mode, we just need to assign one of the mode as a serial shift left, and let's see how the connection is differs. So let's start with this thing, right? This is scan out now for the shift right. This is, let's say, scan out for the shift left, which is connected to the Q1 and Q0 this way. So now I have this mode 0 0 as a hold and 1 1 as a serial shift left. So we first the hold 0 0 terminal 0 is we need to feedback from the corresponding flops to itself. So terminal 0 is connected with the Q of the flip-flop of the corresponding flip-flop. And then scan in for the serial shift right, it's the same thing as the previous one. We connected to the terminal 1 of the multiplexer, and then Q1 is connected to the terminal 1 of the multiplexer for Q0 flop. So that's the connection we have already seen. And parallel load, we have seen that connection already in the previous slide, D1, D0. it will be loading. Now the serial shift left, which is 1 1, that means my terminal 3 needs to be selected in certain ways. So what I do now, scan in, same scan in, I send it to 3 for the lower multiplexer, which will be driving it loaded into the lower flip-flop for the Q0, and output of the Q0 is now connected to the terminal 3 of the upper multiplexer, which will then in turn goes to the flip-flop associated with the Q1. So that means your Q0 is flowing towards the Q1, which is practically your shift left. So that's how we can design a shift register with parallel load and shift in the both direction with those two capability, and of course hold is another capability. So we need to use two multiplexer, 4x1 1-bit multiplexer and two flip-flop. So with that we can all extend it to the 4-bit, to then 8-bit, 16-bit, 32-bit, 64-bit, 128-bit is the same way. It has just this number of components there.